5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
This is About Space, America's return to space, with news and information on our U.S. space program. Is your host of About Space, David Denard.
Welcome, and thanks for joining me today. Gravity. We don't think of gravity very much at all, yet it's the stuff that keeps us from flying off the planet Earth. Well, recently, scientists now believe that gravity moves with a specific speed. But just how fast is gravity? Next, as America and the world is listening to About Space today. Come to the land of orange groves and palm trees. Come to the land of theme parks. Come to the land of sunny beaches and the azure waters of the Atlantic Ocean. So come and visit Florida for lasting memories. Email us. Email david.ddcruisandtours@gmail.com or call D&D Cruise and Tours at 877-747-8631 for your next family, cruise, or theme park vacation. Let us provide you your next visit with our travel experience, not experimentation. We are members of IATAN and CLIA. Email david.ddcruisandtours@gmail.com. Serving the Southeast, traveler since 1985. Welcome back. Dr. Don Lincoln describes a fascinating observation that definitely measures the speed of gravity.
Gravity is the force that holds the universe together. Like the galaxy in which we live, it seems to be eternal and unchanging. However, our current understanding of gravity paints a rather different story. Gravity can bend and twist the shape of space itself, and, if that's true, then it's very interesting to ask how quickly those distortions can move. In its simplest form, the question is, how fast is gravity? Let's look into it. The speed of gravity is a question that has puzzled scientists for centuries. The first sophisticated theory of gravity was developed by Sir Isaac Newton and first published way back in 1687. According to Newton, gravity was transmitted everywhere across the universe at infinite speed. However, Newton's theory of gravity isn't the newest and most successful theory of gravity. In 1915, Albert Einstein published his theory of general relativity, which interprets gravity as the distortion of both space and time. In his theory, these distortions could change the shape of things like stars and planets, and, of course, space itself. These changing distortions would then move through the cosmos by means of a phenomenon called gravitational radiation. He postulated that the speed of gravitational waves was identical to the speed of light. Thus, Einstein would say that the speed of light and the speed of gravity are the same. So who's right? Well, Einstein and Newton are both strong contenders in any contest for the title of most influential physicist of all time. I mean, I would pay good money to watch those two guys debate, but when you get right down to it, it doesn't much matter what either of them think. Physics is an empirical science, and answering the question requires a measurement. So how would you measure the speed of gravity? Well, first and foremost, you need to be able to detect gravitational waves, and that's hard. Gravitational waves distort the size of objects. For instance, if gravitational waves passed over you, they would change your height and width. Your height would shrink and width increase, and then the opposite, with height increasing and width shrinking. And that cycle would happen a few times as the gravitational wave passed over you. That's the basic idea, but do they exist? Einstein predicted they existed way back in 1916, but it took basically a century for scientists to both devise a credible methodology and then develop the technology to do it. Well, gravitational waves are made when any massive object moves. Most waves are ridiculously tiny. The only known way to get big gravitational waves is to rapidly move objects with both tiny volumes and the mass of stars in an oscillating way. That just sounds crazy hard. However, nature is way ahead of us. The universe is full of stars, and many star systems consist of not one star like our solar system, but rather two. And of course, some of these star systems were formed early in the universe, long before our own star formed some 4.5 billion years ago. So these super old stars have lived and died, and some of them are now black holes, which are just long dead massive stars. So, being able to detect gravitational radiation is super important, but it doesn't tell us how fast gravity actually moves. I mean, you do get some information from when the gravitational waves pass over the various detectors arrayed across the Earth. For instance, the distance between the two American LIGO detectors is 3,000 kilometers, or about 1,900 miles. If gravitational waves wash over the Earth, they'll hit one detector first and then the other. And you can use the time difference to get a handle on the speed of gravity. But the time difference also depends on the orientation of the Earth when gravitational waves pass through the Earth, so it's not so precise. And in the fall of 2017, we got lucky. The Earth's gravitational wave detectors detected the passage of a gravitational wave. And about 2 seconds later, orbiting telescopes detected a brief pulse of gamma radiation coming from deep space. After some analysis, both gravitational wave detectors and telescopes agreed that the source was in the same location in the sky, which was eventually nailed down to being an elliptical galaxy in the constellation Hydra called NGC 4993. NGC 4993 is located about 144 million light years from Earth. Given that we know the speed of light, that means that the collision occurred 144 million years ago. Furthermore, the gravitational radiation and gamma radiation were emitted almost exactly at the same time. From this event in which light and gravitational waves were nearly simultaneously created, we can get very precise handle on the speed of gravity. They both traveled for 144 million years. That's 4.5 times 10 to the 15 seconds. And the two pulses arrived within 2 seconds of one another. And from this, we can say with extremely small uncertainties that gravity moves at the speed of light. The difference is, ballpark, less than 1 part in a quadrillion. So there you have it. Using what is called multi-messenger astronomy, which is when researchers combine information from different kinds of detectors, we now have a very precise measurement of the speed of gravity. Einstein's conjecture back at the beginning of the 20th century was true.
Dr. Don Lincoln. Interesting to learn about gravity. And I'm glad to know that gravity is keeping my 2 feet on the ground. And let me remind you to check out our Facebook page at aboutspace.today for launches and landings, and invite your family and friends to listen weekly. Join Don Meyer, Space Coast News Editor, this Friday for America in Space. And to all our listeners around the globe and here in the U.S., thanks for joining me. I'm David Denault, and this has been About Space Today.